Welcome to the Deep Dive. We're the show that takes complex topics and, well, really boils them down to the core insights you need.
Trying to cut through the noise.
Exactly. And today, we're diving into something pretty amazing. The world of molecular architecture. I mean, imagine trying to build something unbelievably precise, like designing a skyscraper down to the very last bolt, but doing it at a scale you absolutely cannot see. We're talking molecules. Specifically, how chemists manage to create carbon bonds with these exact, perfect 3D arrangements.
Sounds like magic almost.
It kind of does. So our mission today is to give you that shortcut to understanding two really groundbreaking chemical reactions. You might have heard of them. Asymmetric Negishi and Kumada couplings.
Big beams in chemistry.
Yeah, big names. We're going to pull out the most important stuff from the research, show you how they work, and crucially, why they matter so much for creating the complex functional molecules that, actually impact our lives.
That's absolutely right. And you really need to get this.
Yeah.
This isn't just abstract chemistry happening in a flask somewhere.
Right.
These reactions, they're fundamental, foundational even, to everything from developing new medicines that save lives to creating advanced materials that, well, improve our world.
Okay.
And a key idea here, maybe the central idea, is chirality. It's like molecules can exist as mirror images of each other. Think of your hands. They look the same, but they're mirror images.
Right.
You can't superimpose them.
Left and right hand. Yeah.
Exactly. And in biology, often only one of those mirror image forms, one hand, will actually work as, say, a drug. The other one, it might be useless or sometimes even harmful. So getting that specific shape, that precision, is absolutely paramount.
Okay, let's unpack that. This idea of precision in building molecules. So you're saying a huge challenge in organic synthesis, which is basically the art of building molecules, right?
Oh, it is.
Is forming those carbon bonds, the backbone of pretty much everything organic. But doing it with super precise control over the 3D shape.
Yes, exactly. It's like needing to place a specific Lego brick, not just in the right spot, but at exactly the right angle, facing the right way, every single time. No mistakes allowed.
Wow.
And to get that kind of precision, chemists use tools called enantioselective and enantiospecific reactions. Now, enantioselective reaction, it takes starting materials that maybe don't have a specific handedness, the aquile, or they're just a 50-50 mix of both mirror images, called racemic.
A jumble.
A jumble, yeah. And the reaction cleverly creates a product that is mostly, sometimes almost entirely, just one of those mirror image forms. It's like creating the specific handedness you need.
Okay, creating it. And the other one, enantiospecific.
Right. Enantiospecific is a bit different. You could call it a chirality exchange process. Here, you start with a molecule that already has a specific 3D shape, a defined handedness. And that existing shape, that chirality, directly controls what the product shape will be. The original handedness is either kept the same retention or flipped inversion, but always in a predictable, controlled way. You know exactly what you're going to get based on what you started with.
So what does this all mean for you listening?
Well, here's the kind of aha moment, right? This incredible precision is critical because so many important molecules, especially bioactive ones, think pharmaceuticals, they absolutely need to be in one specific mirror image form to work properly, or, just as importantly, to avoid nasty side effects.
Absolutely critical. The wrong shape can be a disaster.
So these specialized reactions, Negishi, Kumada, they're the sophisticated tools chemists use to build molecules with these incredibly specific 3D arrangements, whether it's, around a central point or maybe along an axis like a screw thread or even within a flat plane.
Precisely. They offer exquisite control.
Okay, this is where it gets really interesting, I think. Let's dig into the origin story. The Negishi coupling. Where did this come from? Well, this groundbreaking work really gained momentum back in the mid-1970s. The key figure was Eiichi Negishi, who was at Syracuse University at the time. His big goal, his quest, was to find new ways, milder ways, to stitch together these vital carbon bonds.
Milder being important, I guess. Less harsh conditions.
Yes, exactly. Easier to handle, more compatible with complex molecules. Now, Negishi's early studies were revealing. He noticed something crucial. When he used nickel catalysts, which were common, then the precise 3D structure, the stereochemistry, often got scrambled.
So it wasn't precise enough.
Right, it deteriorated. But then he tried palladium catalysts, and boom, the precision was beautifully maintained. The 3D shape stayed intact.
Okay, that's a key observation.
Huge. This insight led him to pivot, to try using organozinc reagents coupled with these palladium catalysts, and that led directly to his, seminal 1977 paper. He showed how you could efficiently make these complex, unsymmetrical molecules by coupling aryl zinc compounds with aryl halides using palladium. It just worked beautifully.
And the impact of that work?
Oh, profound. Absolutely profound. Negishi, along with Heck and Suzuki, shared the 2010 Nobel Prize in Chemistry, specifically for palladium-catalyzed cross-couplings in organic synthesis.
Wow, Nobel Prize level stuff.
Definitely. It cemented the Negishi coupling as a cornerstone, a real pillar of modern organic synthesis. Its versatility is just amazing. It can link up different types of carbon atoms, sp2 with sp2, sp2 with sp3, even the tricky sp3 with sp3.
Which means
It's incredibly useful across the board. Pharmaceuticals, new agricultural chemicals, advanced materials, science. It's everywhere.
Got it.
And actually, it's worth pointing out, the very first asymmetric Negishi coupling, the first one that created that specific handedness we talked about, was actually reported a bit later, in 1983 by Kumada's group.
Oh, interesting. Kumada getting in early on the asymmetric side.
Yeah, they managed an impressive 86% in antiomeric excess, or E. That's the measure of how much more of the desired mirror image you get compared to the unwanted one. So 86% E was pretty good going back then, showing early promise for controlling that handedness.
Okay, so palladium was the star initially, but now let's talk about nickel again. You said it had issues early on, scrambling the shapes.
It did.
But it's made a huge comeback, especially in these asymmetric shape-controlling reactions.
It really has. It's a fantastic story of, scientific persistence and innovation. Nickel, which Negishi initially moved away from because of those stereochemical problems, has reemerged as an incredibly powerful catalyst, particularly for these tricky asymmetric transformations.
How did that happen?
Well, a lot of credit goes to research groups like Greg Fu's starting around 2005. They really spearheaded this nickel renaissance. They showed nickel's incredible versatility, working with all sorts of different starting molecules.
Like what?
Things like alpha-bromoamides, complex secondary benzylic halides, molecules that weren't easy to handle before.
Yeah.
And they were getting really high enantioselectivities, often over 90% E.
How? What was the trick?
The key was designing very specific chiral ligands. These are helper molecules that bind to the nickel. You can think of them like molecular gloves that guide the reaction, forcing it to create predominantly one mirror image.
Like a glove forcing your hand into one shape?
Sort of, yeah. And what was really clever was the stereoconvergent nature of many of these reactions. You could start with that 50-50 racemic mixture, the jumble, and the nickel catalyst system would funnel both starting mirror images into mostly just one desired product mirror image.
Yeah.
So it wasn't just selective, it was actively converting the unwanted starting material too.
That is clever. Taking a mix and getting one outcome.
Exactly. And understanding how it worked, the mechanism, was key. Computational studies, like DFT calculations by Lin's group, suggested a specific Nakite catalytic cycle was operating. Knowing these details helps chemists design even better catalysts.
And did this have real-world uses?
Oh, absolutely. For instance, Fukuyama used this nickel methodology as a key step in synthesizing a complex natural product called daphnylene. They got a crucial intermediate piece with 94% E. That's high precision.
Okay.
And Fu's team just kept pushing, systematically. They expanded it to work with propergillic halides in 2008, getting up to 93% E. Then alpha-bromide trials in 2012, up to 94% E. They even pioneered the coupling of really challenging racemic secondary allylic chlorides back in 2008.
Allylic chlorides, okay.
Yeah, getting up to 96% E. That opened doors to making complex structures like another natural product, fluvarucinine-A. They were just relentlessly broadening the scope.
It sounds like they were systematically taking on harder and harder challenges. What about really stubborn starting materials?
Yep, they tackled those too. In 2013, Fu's group showed they could use nickel for unactivated secondary alkyl electrophiles, things that usually don't want to react nicely to make chiral pyrrolidines, important ring structures in medicines, again with high E. The secret there was ensuring the final bond-forming step, the reductive elimination, was tightly controlled by the catalyst. They also figured out how to make enantiomer-enriched level 1 diarlocanes, which are precursors for drugs like the antidepressant Zoloft. That involved managing short-lived radical intermediates and ensuring rapid equilibration to favor the desired product.
So understanding the reaction pathway, even the fleeting steps, was crucial.
Absolutely. And the innovation didn't stop with Fu. Other groups jumped in. Doyle developed nickel methods for making complex nitrogen-containing rings in 2013. Fu came back in 2014 with breakthroughs for making valuable fluorinated molecules from alpha-fluoroketones up to 97% E, and also working with alpha-bromosulfonamides and sulfones, again, very high precision.
Fluorine is important in drugs, right?
Very important. It can dramatically change a molecule's properties. And then in 2019, Fu tackled alpha-halosolanes, broadening the scope even beyond typical carbon-based electrophiles.
Wow, okay. Any very recent stuff.
Oh yeah, the field is moving fast.
Yeah.
In 2023, Barron developed an enantioselective decarboxylative cross-coupling, using nickel, a totally different way to make complex alcohols involving radicals. Liu's group, also in 2023, found ways to make tricky four-membered rings called cyclobutanones with up to 98% E.
Four-membered rings are tough.
They are. And just this year, 2024, Otter Low reported an atroposelective Negishi coupling, controlling that axial twist we mentioned, to make anti-cancer natural products, solving a major synthetic puzzle with up to 96% E. Wang developed methods for tricky SCRs containing tertiary stereocenters, and Liu, looking ahead to 2025, published a breakthrough using nickel for defluoroalkylation to make chiral defluoromethyl-containing isobenzolinones again, important structures for pharma and agrochemicals, likely using that NET3 cycle.
Incredible. The pace is just relentless. Nickel really went from like 0 to hero in this area.
It really did. A testament to catalyst design and mechanistic understanding.
Okay, so nickel's had this amazing resurgence. But let's not forget palladium, you said as the original star. Is it still playing a key role in these high-precision asymmetric Negishi reactions?
Oh, absolutely. Palladium hasn't gone away at all. It continues to be a workhorse, often pushing the absolute boundaries of selectivity.
Okay.
For example, back in 2006, Espinet's group used palladium for asymmetric Negishi couplings to create complex, sterically crowded binaphthalene derivatives molecules, with that twisty axial chirality getting up to 85% E. The key there was, again, a stereoconvergent pathway. The chiral ligand on the palladium dictated exactly which face of the molecule reacted during that final bond-forming step.
So even with bulky molecules, palladium could control the outcome.
Precisely. And fast forward to 2022, Liu's group used palladium in a highly optimized synthesis of a potent KRAS G12C cancer inhibitor called GDC6036. What's interesting there is that they combined high-throughput experimentation HTE, basically running tons of reactions quickly with computational analysis to really fine-tune the system for this complex drug target. That shows how these methods are being industrialized.
Right, integrating tech to speed up discovery.
Exactly. And some really cutting-edge palladium research just came out in 2024 from Wang, Hong, and Shi. They developed a palladium-catalyzed enantioconvergent Negishi for making those 11-1 diethylalkenes we mentioned earlier precursors for drugs. They achieved yields up to 99% and E up to 91%.
Very efficient.
Extremely. The key there was using bulky chiral and heterocyclic carbene ligands, NHCs, on the palladium. These seem to enable a dynamic kinetic resolution during the transmetallation step, where the zinc reagent transfers its group to palladium. Basically, the unwanted mirror image could convert to the desired one before it reacted.
Ah, another way to maximize the yield of the right product.
Exactly. And speaking of understanding mechanisms, Maline's group published computational work in 2024 showing something fascinating. In one system they studied, lower than expected enantioselectivity wasn't because the chiral ligand wasn't doing its job well, but because the ligand was sometimes falling off the palladium temporarily during the reaction cycle. That loss of contact meant a loss of chiral control. Understanding those subtle details is just vital for designing the next generation of catalysts.
That's a fantastic insight. It's not always what you think. So we've covered nickel's comeback, palladium's precision. Now, you mentioned cobalt briefly earlier. It sounds like it was maybe an afterthought. Is it becoming a player now, too?
It definitely is. Cobalt used to be sort of overlooked for these specific couplings compared to nickel and palladium, but it's really emerging as a powerful and sometimes complementary catalyst, particularly for reactions involving radical intermediates.
Radicals. Okay, so a different mechanism sometimes.
Often, yes. A landmark paper came from Walsh's group in 2018. They reported the first cobalt-catalyzed enantioselective Negishi coupling, specifically using racemic alpha-bromoesters as starting materials. They got excellent yields, up to 98%, and really high enantioselectivity, up to 97% E.
First cobalt one, that's significant.
Very. And it operated through a radical-based pathway. They even showed its practical utility by synthesizing a natural product, R-xanthorezole, on a gram scale, which is important for showing it's not just a tiny-scale curiosity.
Right, scalability matters. Any impact on medicines.
Directly. Zhang's group applied this cobalt chemistry to synthesize key pharmaceutical intermediates. For instance, S-preclamal, which is a dopamine receptor agonist, potentially useful for neurological issues, and also arsenicalcet, a drug used to regulate calcium levels in patients with kidney disease.
Wow.
And for cinecalcet, they actually used recrystallization after the reaction to bump the E up to over 99%, basically optically pure. That's often a necessary step for pharmaceuticals.
Okay, so cobalt is finding its niche. Any newer cobalt work?
Definitely. Liu's group in 2023 developed cobalt methods using more stable benzyl chlorides to make those 11-on-1 diromethanes. And very recently, in 2025, they turned to alpha-bromoctones, again using cobalt, achieving high E, up to 94% with carefully designed ligands.
Ligand design seems to be the key everywhere.
It really is. And building on that, he and Liu, also in 2025, expanded the scope to alpha-bromo, alpha-fluoroketones using cobalt. This was the first cobalt-catalyzed asymmetric Negishi that could create these really valuable acyclic quaternary alpha-fluorocarbonyl stereocenters. Basically, a carbon atom bonded to 4 different things, including a fluorine with high precision, up to 92% yield and 98% E. Again, driven by smart ligand design.
Amazing. Cobalt is clearly stepping up. Okay, we spent a lot of time on Negishi. Let's shift gears. You mentioned Kumada earlier, the Kumada coupling, another pillar for CC bond formation.
Absolutely. Just as important in many ways. The Kumada coupling uses Grignard reagents organomagnesium compounds instead of the organozinc reagents used in Negishi.
Okay, different metal reagent. History there.
It actually has a longer history in some ways. Early related work goes back to Karash and Fields in 1941 using cobalt. But the modern era really kicked off in 1972. Independently, 2 groups, Koreas in France and Kumadas in Japan, reported using nickel catalysts effectively. That was a big step up.
Nickel again early on.
Yep. And then Murahashi introduced palladium catalysts for Kumada couplings in 1975, broadening the options further.
So nickel was involved early, just like with Negishi. Did Kumada also do asymmetric versions?
He did. In 1976, Kumada reported the very first asymmetric Kumada reaction. Pretty early days for asymmetric catalysis. He used chiral ferrocinyl-based ligands built around an iron sandwich structure, and achieved up to 63% E.
Okay, maybe not super high E by today's standards, but pioneering.
Exactly. And importantly, he demonstrated the concept of kinetic resolution of the Grignard reagent itself, meaning one mirror image form of the magnesium reagent reacted faster than the other, allowing for enrichment.
That's neat, resolving the reagent. What about understanding how these Kumada reactions work?
More recent work, particularly by Fu's group again, has shed light on that. In 2010, they developed a nickel-catalyzed asymmetric Kumada for alpha-bromoctones that worked even at very low temperatures like minus 50 degrees Celsius, getting up to 95% E.
Minus 50.
Yeah, remarkable control. And later, in 2019, Yin and Fu did an in-depth mechanistic study. They found that while radical intermediates are definitely involved, like in some Negishi reactions, the final enantioselectivity, the actual 3D control, often comes down to that final reductive elimination step, where the product is formed and released from the nickel. And that step is controlled by the chiral ligand. Knowing this helps design better ligands for future reactions.
So the endgame is crucial for the shape. Any other recent Kumada finds?
Yes. Mazet's group in 2025 studied the nickel-catalyzed Kumada coupling of beta-bromostyrenes. They achieved high selectivities and uncovered some fascinating mechanistic details, like a dinuclear nickel species being the resting state, and evidence for dynamic kinetic resolution happening.
Always more to learn about the mechanism. What about cobalt and palladium in Kumada?
They play roles too. Walsh's group, who did the first cobalt Negishi, also reported the first cobalt-catalyzed asymmetric Kumada in 2014. They got great yields in E, up to 97%, and used it to make pharmaceuticals like the anti-inflammatory drug S-phenoprofen.
Cobalt again proving useful.
Yep. And Zhang's group in 2020 used cobalt Kumada with alkynyl Grignard reagents, achieving up to 95% E, and applied it in syntheses related to insect pheromones. On the palladium side, Richards used a ferrocene-based palidocycle catalyst in 2022 to make enantio-enriched biorols via Kumada coupling, getting up to 80% E.
So all 3 metals, nickel, palladium, cobalt, are valuable tools for both Negishi and Kumada asymmetric couplings.
Exactly. Each has its strengths and preferred reaction types, giving chemists a powerful toolbox.
Okay, let's circle back to something you mentioned earlier, enantiospecificity. That idea of transferring existing chirality, preserving the shape.
Yes, this is really elegant chemistry. Instead of creating chirality from scratch or from a mix, you're precisely relaying it from the starting material to the product.
How does that work in practice? Any examples for Negishi or Kumada?
Sure. For Negishi, groups like Campos's and Baudouin's developed methods to prepare an NeoPure zinc reagents starting materials, where essentially 100% of the molecules have the desired handedness. Then, they performed a PD-catalyzed Negishi coupling that proceeded with stereo retention, meaning the product perfectly retained the 3D arrangement of the zinc region.
So perfect transfer.
Pretty much.
Yeah.
But maybe one of the most significant contributions in an NEA-specific Kumada coupling comes from Jarvo's group. In 2014, they reported a major advance in stereospecific nickel-catalyzed coupling for making C-sp3 bonds.
C3sp3, that's the tough one you mentioned.
Exactly. It's difficult because of side reactions, especially one called beta hydride elimination, which can just destroy your product or scramble the stereochemistry.
Right.
Jarvo's team meticulously optimized the nickel catalyst system, the ligand, the additives, and they achieved incredibly high aneospecificity, often over 99% A's, which is the measure for specific reactions. Essentially a near-perfect transfer of the 3D information. But importantly, it happened with inversion of configuration at the reacting carbon center.
Inversion, so it flips the handedness predictably.
Precisely. Like turning a left glove into a right glove, but perfectly. And this wasn't just, an academic curiosity. Some of the molecules they made showed selective activity against MCF7 breast cancer cells in testing.
Wow, direct biological relevance.
Yeah. And they showed that the method was quite general, working for making complex cyclic ethers and sulfonamides too, demonstrating its broad applicability. It really highlighted how controlling these tricky sp3 couplings could unlock access to valuable structures.
That really underscores the power of controlling these reactions down to the finest detail.
Absolutely.
Yeah.
When you pull back and look at this whole deep dive, what really stands out is the immense power and versatility of these asymmetric Negishi and Kumada reactions.
Yeah.
And it's crystal clear that the progress hasn't just happened by chance. It's been driven by relentless advances in designing those chiral ligands and the molecular guides, and crucially, by digging deep into understanding the reaction mechanisms step by tiny step.
Couldn't agree more. And these aren't just, fascinating puzzles for chemists in labs. We've seen the examples. These are indispensable practical tools. They let chemists build the new drugs that treat diseases, the new agrochemicals that help feed us, the advanced materials that shape our technology. They directly improve our lives.
Tangibly improve them.
Yeah. It's quite a journey we've traced from those pioneering discoveries, the Nobel Prize-winning insights, all the way to these incredibly sophisticated modern applications that let us build molecules with breathtaking precision and complexity.
It really demonstrates how that deep, fundamental understanding of chemical reactivity, coupled with continuous innovation and refinement, leads directly to breakthroughs that have a massive real-world impact.
So for you listening, what's the takeaway? Well, maybe the next time you hear about a potential new drug passing trials or some cutting-edge new material being developed, you'll have a bit more insight, a glimpse into the kind of intricate molecular architecture that likely had to be built to make it possible.
Using tools just like these.
Right. It's really a testament to the ingenuity of chemists, constantly pushing the frontiers, figuring out how to build things that maybe seemed impossible just a few years ago.
The progress is astonishing.
It really is. And maybe here's a final thought to leave you with. As catalyst design gets even smarter, and our understanding of these complex reaction pathways gets even deeper, what currently unimaginable molecular structures might chemists be able to construct next? What new functions, what new solutions for humanity might they unlock?
That's the exciting part, isn't it? The possibilities keep expanding.